Well, again, thanks for joining, everybody. Today, we're going to look at a specific challenge. And in this case, it's the challenge of well corrosion and erosion, and how managing this can help extend life of wells and hopefully result in long-term increased productivity and drainage. We're going to look today at some of the factors that affect this, some of the techniques that are available to help understand this, and hopefully we'll see through case studies how we can apply these to hopefully improve the management decisions you have to make. In particular, we'll be looking at a technique we call CorrosionVA. And before we get there, we'll actually introduce visual analytics, which is the V and the A at the end there. And we'll look at the technologies that support that technique and some of the science that sits behind it. And then we'll take a look at some of the applications that we use it for through case studies based on work that we've performed. So corrosion management is a life of well challenge, but there are certain times when it becomes more prevalent than others. And in particular, in later life of the well, or even in mature fields, as we try and eke the last bit of production from these wells. And this is becoming increasingly more important because as the major discoveries become more and more challenging to extract, either in terms of the geology you've got to go through or the economics of actually making them profitable. And again, today's environment makes that even tougher. This places an increasingly growing demand on production from aging wells. So keeping them running, keeping them safe is very important. And ultimately that can lead to good economics. So again, later life management is one of the challenges here that we have to face. And there's a number of regions I could have chosen to illustrate this, but I've chosen to stay local to my home region, and that's to look at the UK and the continental shelf exploration and development work that goes on here. So in this first chart, we can see the age and time across the bottom axes and the number of wells on the vertical axis. Now, what this chart is showing is the number of wells that are still in operation. And by that, I mean they haven't been classified as abandoned. They could be plugged, ready for abandonment. They could be shut in, waiting for repair or some sort of in situ remediation. Or they could be completed and operating and producing, or they could be currently in a drilling phase, ready to be completed later on. But effectively, they're all active wells. And what this chart shows us is the completion date of all of the active wells in the UK sector at the moment. So you can see there's quite a few newly completed wells contributing to the production, but you can also look back here that some of the wells that are in circulation, they've been in effect since the late 60s and early 70s. So when we take a look at that overall, we find that the average age of a well here in the North Sea is about 24 years old. The oldest wells are coming up to 55, 56 years old, which is quite an achievement in many senses. This is more of an achievement given that a lot of these wells are designed with a 15 to 20 year lifespan. So with the engineering efforts and the maintenance we've been able to do, we've gone way beyond the expected life of these wells, and in some cases have got fields continuing in operation well past their expected useful time length. But this in itself is not simple. This comes with a lot of challenges. It places a lot of stresses and demands on structural integrity. And that's made more significant as time goes on, because there's a lot of changes that occur in the well's life, changes in chemistry or forces. And this could come from either a change of use, producer to injector, maybe installing artificial lift, but also with some of the produced fluids and the changes there. And in particular, the increase in water production. So if we take a look at that in detail on the second chart, you can see here the production history for the same sector. And you can see overall that the water content, which is shown in the dark blue, has risen over time. There have been some efforts to reduce that and increase productivity in recent years. But ultimately, it's still quite a water-dominated environment. Some of that naturally produced. Some of it we've actually injected ourselves, enhanced oil recovery and injection wells to try and stimulate production. But in short, the average well is sitting somewhere near 70% water cut. The highest producing well, and again, this is not an injection well, so don't be tricked by that one. This is a genuine hydrocarbon producing well. There are some that are sitting over 99% water cut. So with that, you've got challenges in managing the chemistry there. This water brings with it potentially corrosion-enabling materials. It could carry oxygen, it could carry minerals, dissolved gases, and even things like sediments coming out of precipitation. It could bring sand with it. So again, this challenge of keeping the wells healthy gets more difficult as time goes on. So I guess to conclude that, the main thing to point out here is no matter how hard we try to keep these wells right by design and fit for purpose, it's inevitable that components will fail under these conditions. The key part of the challenge of managing this and moving on effectively is being able to accurately diagnose the issues and take effective and decisive remedial action, which is where we want to start today with visual analytics, and in particular, CorrosionVA. So just to set the scene, I want to introduce visual analytics as a concept. And put simply, visual analytics means quantified vision. By mapping the way the overall optical systems that we deploy manipulate and capture the rays of light, we've been able to calculate a transform function to restore the true geometric properties of any object within the field of view. This enables us to take accurate measurements in situ at the well site of anything that we see. In this example, some hydrates that are formed in this gas producing well, but this could equally be the top of a fish that we're trying to extract from the well. The second example is looking at the side view camera at some micro corrosion events. And you can see here some very small pitting that's occurred in this well. And being able to quantify these and accurately understand their severity, their frequency, and even their changes in time gives us a very powerful system and tool to help manage corrosion and its effective management. You could be monitoring the performance of inhibition treatments, or even if you're looking at sand-induced erosion, how much this is happening and the rate of change, and potentially a time until this becomes critical. So with this information, we get a lot of information. You can see the exact root cause of the problem, its location, its extent, and the severity of it. So with that, we believe that quantified vision and visual analytics, as we call it, gives a very detailed understanding of the well conditions. But it's not just through the images alone that we can acquire information. We actually use the combination of conventional logging technologies with the video to give an augmented view of the world. So providing combinations of images and other sources of log data, we can get more out of the well and understand it in greater detail. And in this example, we're showing the combination of video with multi-finger caliper with a system that we call the integrated video caliper, or IVC for short. So you can see it had a 24-arm caliper in this example, combined with a sideways viewing camera and a downward viewing camera, providing high frame rate, high definition images in real time. The system can be configured in memory mode, so it can run on any mode of conveyance, whether it's E-line, coil, electric tractors, or even fiber or electrically enabled core tubing. And while this combination service provides a gain in efficiency at the well site, doing 2 trips and condensing that into one, the main gains are in what we can do with the information that we derive from it, and how analyzing those data sets in combination allows us to understand issues in much greater detail through that combined analysis. To help us with that and to achieve the goal that we wanted, EV acquired a specialist well integrity software and analysis company called Epidote back in May of 2016, so coming up for 4 years ago now. And Epidote are a specialist developer and licenser of the widely used multi-finger imaging processing software suite, or MIPS for short. And this can be used for caliper and thickness data. License holders include operating companies and service companies, and we continue to distribute and maintain licenses and support those license holders with training, guidance, and even consultancy for complex operations. We also act as an independent advisor. So if there is any concerns over a particular analysis, we can have a look at that as an independent body and give feedback to suit. But this example shows MIPS Pro in action and some of the features we have there, that we can look at the two-dimensional data on screen with the caliper, individual traces, the pipe statistics. We can also look at thickness data in combination with that, and we can break it down statistically or even view it in 3 dimensions if we like. All of this is interactive, and you can drill down through the data to really dissect and understand what's going on inside the well. And building on that, we also have the PIP platform, or the pipe integrity platform. And this takes what we did with MIPS and adds in a lot of extra functionality to give a comprehensive cased hole analysis suite. So this would include the addition of spectral acoustic tools, cement evaluation, magnetic flux leakage, multi-barrier pulsed eddy current technologies, and a whole host of file handling and display updates to handle that additional data set. But in short, no matter what the combination of services that you've run, be it in one run or multiple trips, we can combine that and analyze them jointly. And it's really through these Epidote products that visual analytics has been powered and delivered to the service industry today. Just as a quick example, this is what we can do with that combination of services. And here we're looking at a data set from the integrated video caliper. We're actually looking at the insert profiles for a subsurface safety valve. And you can see on the caliper data, the profiles where items will be set and the control recesses and the likes. You can see that displayed as a 3-dimensional object on the right-hand side here, and you can manipulate that view to any position that you like. But with the addition of the video system, we can also embed images and video sequences on depth at areas of interest and across the entire logging interval. And what that allows us to do is not only quantify what we're seeing with the caliper, but we can also see it qualitatively and quantitatively with the images at varying depths. In this last sequence, you're seeing a selection of 360-degree panoramic images that we've taken with the side view camera at specific profiles of interest inside the well. And we could take that a step further with the animation on the right-hand side and look at that in 3 dimensions. Here we've taken one of those 360-degree images and we've superimposed it on top of the geometry recorded by the multi-finger caliper to show a picture in the true shape and form that it occurred downhole in the well. And we can also take some spot measurements at varying points so we can understand the size and severity of anything that we see in there. But in this case, you can see a lot of corrosion and surface pitting that's occurred in these recesses. In this case, the control line recess of this safety valve insert. This explained why the operator was having such difficulty setting a wireline retrievable safety valve. They were losing pressure through the control line, and we helped diagnose that it's actually the recesses and the condition of the well itself. So with that, they then had to switch to an alternative plan, work the well over, and potentially then get the well back and reinstated. So there are a number of different challenges and applications that we can apply this technique to. But today we're going to concentrate, as we said, on CorrosionVA and how we can use the information here to try and help extend the life of wells and maintain safe functional operation. To illustrate that, the best thing to do is really look at a series of case studies. And the first one I want to walk you through today comes from an offshore operator in the Mediterranean off the coast of North Africa, who was operating a high pressure, high temperature gas condensate field. Now, they performed a check of their safety valve performance, but unfortunately, they were having issues in getting that to seal. In fact, they weren't entirely sure whether it was moving at all, whether there's any functionality of the system, whether the flow tube was moving or whether the flapper was moving successfully. They tried to reactivate that valve with some cleanup runs, thinking it could have been scale and deposition or something along those lines, without any success. So without wasting too much time, they then switched to an alternate plan of trying to set a wireline retrievable safety valve in a profile not too far away from the main safety valve. Unfortunately, they had issues in getting that to set successfully. Very similarly to the last case study, it was leaking pressure, and that was found to be at the lower seal bore through a little bit of investigation work. And at that point, the operator chose to call out some investigation services and try to understand what's happening downhole. But just to give you an illustration of what the safety valve should look like when it's operating correctly, I've just put a little video in here on the right-hand side as we're looking down through the flow tube that's moving up with the tool stationary, nice smooth motion. And then when we get to the right position, it allows the flapper to swing shut and then isolate the flow from below. So that's what it should look like. And again, with the high quality video that we've got, you can see that very smoothly and very clearly. Everything in that case was working perfectly and a good seal had been established. But when we came to look at the well in question, we actually found a few problems that you couldn't really have diagnosed of any other means than this combined caliper and video combination. First of all, we looked in detail at the permanent safety valve, the one that was installed with the completion. And when we got to see the system perform, we found that the flow tube was actually operating perfectly. It was moving very smoothly, no issues there at all, but the flapper was remaining rigid. We then went down to have a look at that in detail. And what we found is that the spring that connects the flapper and activates it, you can just see here, has actually got a break in it. It's actually parted there and lost all of its spring force. You can actually see the flapper just below it here, this circular object. So knowing that, it was fairly clear that this valve couldn't be reactivated and reinstated, and that the insert was the next best thing. So we turned our attention then to diagnosing why the insert valves were having issues and why the seals weren't setting at that lower seal bore. First of all, we took a detailed look with a multi-finger caliper, and we recorded all of the profiles and geometries around the insert section. And you can see here the different step changes, the different recesses as we work through the assembly. These were then matched up with an engineering drawing of the valve in question, and actually everything looked fine. The dimensions that we'd captured looked very close to those of the manufacturing drawing and was certainly within tolerance for accepting the insert valve. But it's when we then switched back to the video and we looked at the seal bore surfaces in a lot more detail, we then understood the problem. And that was a series of quite extensive vertical scratches running along the surface of that seal bore. Now, these could have been caused by a number of different things, but the most likely cause would be previous wireline interventions and the abrasion from the cable. But knowing that, it became clear that the surfaces here were too badly affected to accept the seal, and that an alternate strategy was going to have to be taken. There was talk of actually putting an insert valve in regular tubing by potentially punching that and looking at it that way, or it could have gone to a workover, and we're still waiting to hear the results of that. But ultimately, the strategy that they had of trying to reinstate operation with an in situ repair was not going to be possible, and that allowed them to move on quickly to assess alternate techniques. Our second case study, again, comes from a similar part of the world, but in this case, the operator is trying to understand a particular problem that they thought was linked to a failure of a jet pump providing artificial lift in their well. At some point during the production, they noticed a sudden decline and also some bottom hole and annular pressure anomalies. Again, looking at the most likely candidates, they thought this could have been the jet pump and its housing may have failed. So to try and diagnose that, EV recommended the use of the IVC system, very much as we saw earlier on. And we'd use the multi-finger caliper to assess the overall geometry and condition of the pipe and the housing itself, but also the video elements to understand in detail what the surfaces look like and if there are any small anomalies in there. And what we found when we looked at the video was a pinhole that had developed in the housing of the jet pump. And you can see the image here very clearly. We were then able to dimension that at the well site in real time. We took measurements of it and found that it was approximately 0.6 of an inch or 15 millimeters in diameter. You can also see the cross-sectional area there as well. We then looked at the overall geometry with the multi-finger caliper, and you can see here, as highlighted by the cursor, the location of that small hole in relation to the rest of the assembly. And there it is on the 3D view as well. We also took a detailed look at the surrounding area with the side view camera, and we noticed a few other things in there. There's some general erosion around that assembly, but also we found the presence of quite a bit of precipitation, some scaling that had occurred in there. But the best thing about this really was that there was only one confirmed anomaly. There was only one hole in that housing, and the multi-finger caliper confirmed that overall the rest of the well and the rest of the completion was in very good integrity and good shape. So with that, the operator was able to develop a modified jet pump where they repositioned the seals to isolate the hole in the jet pump housing and install functionality and integrity. And with that, they were then able to put the well back onto production, and it's been producing perfectly well ever since. So in this case, a much better outcome that with the downhole diagnostics led to a solution that was effective and enabled an in situ repair. In this case, the operator was delighted because when we look at the overall impact and economics of this, you can see a significant cost saving for doing the in situ repair and diagnostic surveys compared to having to go to a full-blown workover. And this takes into account not only the rig costs and the recompletion costs, but also some of the deferred production and time saved in having to do that. And more specifically, looking at the diagnostic surveys, by combining the multi-finger caliper and the video into a single run, we saved roughly 2/3 of the time of a conventional operation. So a single, very effective, very time-efficient operation gave the answers that were needed at the well site, affected a decision, and enabled an immediate repair and modification within a few days. So a very successful operation overall. But moving on, we're constantly developing technology at EV. We have a passion for innovation, and it's at the heart of everything we do. And since we performed that operation, we've released a new camera technology that we call Optus Infinity. Now, Optus Infinity is the culmination of many years of dedicated research to deliver the world's first array side view camera. You can see in here that it's comprised of a modular down viewing camera that can be disconnected if required. But the real brains of it is what happens in the middle with the array itself. And here you can see 4 azimuthally aligned video systems, all recording together at the same time to give 100% coverage, a full 360-degree video image around the well surface. That, coupled with some advanced image processing techniques, allows us to join those 4 video feeds together to give a continuous single 360-degree view of the well in very, very high resolution and ultimately infinitely long if we choose to do so. This is a real step forward because now instead of having to direct and angle a side viewing camera on demand, we're capturing that full 360-degree view all the time. which enables us to use this system like a regular logging tool that you run in and out of the well, recording as you go and capturing information in a continuous motion. So just to round that off and show how we can use this technology, this image that we're showing on the left-hand side comes from a well in North America where an operator had been experiencing sustained annular pressure. And by doing tubing integrity tests, they ruled out any problems with the tubing itself. So then came to the conclusion, this must be a casing hole and potentially some gas coming through from a shallow formation. So they pulled the completion to work over the well, ran a few diagnostic surveys, including the camera, and we found very, very quickly the hole that you can see here on the left-hand side. And this image has been combined from all 4 video feeds to give that 360-degree view around the well bore. On the right-hand side, you can see the measurements that we took, again, at the well site, showing that this is roughly 1 3/4 inches long, 2 inches across the longest diameter, and about 3/4 inch to 0.8 inch wide. You can also look at the cross-sectional area of that if you wanted to, but ultimately you can understand the size and extent of the problem. But from the rest of the images, you can see very clearly that the well otherwise is in very good condition. There aren't any other pits or points of leakage that are broken through. This seems to be an isolated event. So with that, a relatively simple operation, a little cement squeeze there to isolate it, and the inflow test showed that this was actually holding. Well recompleted and put back onto production. But just to show how we can view this and the interactivity that we get from Optus Infinity, this final sequence shows us turning it into a 3-dimensional object and viewing that from any angle or any orientation that we like. So again, we don't just have to look at this as a single static object. We can turn this into a cylinder. We can put the data on top of multi-finger caliper measurements, and we can then display it back in its natural form, helping to make easy, simple decisions based on information that you can see and measure. So there we have it. That's really all I had for you this morning or this afternoon, depending where you are in the world. But to summarize, I wanted to really close by saying that this application of visual analytics and visual data has transformed the way we can use downhole video. The sheer volume and density of the data that we're capturing gives us incredible high definition and the ability to resolve even the smallest problems that otherwise wouldn't be possible with conventional techniques. And this in itself has led to a fairly rapid expansion of the types of applications that we can use it for. We've shown today some corrosion studies, but we're also using this for investigating sand control problems, looking at screens, potential sites of sand breakthrough and erosion. We look at perforations, their condition, whether they've become plugged up over time with deposits, or even if the original charges have performed to the desired status. We can also use that to help optimize hydraulic fracturing as well. But again, all of these different items, whether it's investigating the source of water entry or looking at leaks, these are things that we can see very, very clearly, give you a very detailed understanding of what's happening, and hopefully get you one step closer to solving and resolving the problem. So with that, just a few quick notes. A lot of the information that we showed today was taken from an SBE paper. So I put the number up here again in case you wanted to jot that down. And really, if there's anything in here that you're interested in, the Q&A session that's coming up, that's what we'd love to discuss with you. Are there any challenges that you face? Are there any questions you have about the techniques and technologies? But if we get to the end of the session and you come back and you think, God, I wish they'd spoken more about this, the best way to get in contact is through our website. You can use our sales email address, or if you visit the website, you'll find a local contact person listed on the homepage. Now, this is sensitive to where you are in the world. it will work out where you are and where the location of our nearest person is. So it should come up with a nice local contact there. In this case, I get the lovely Michael Emsley, who's sitting just down the road from me in his home office today. So with that, I'll wrap things up. I'll say thanks again to everyone for dialing in and for your time, attention, and interest in today's session. And if you have any questions, then please feel free to ask them, and we'll do our best with the team assembled today to help answer them. Okay, so any questions from the audience?
There's some question in the chat, Mike.
Yeah, we've got a few questions here in the chat window. So firstly, from Longi, asking if there are any case studies where the IVC wasn't particularly helpful. And a second question from Didier asking if we could clarify the type of fluid required to get that quality of video.
Yeah, great questions, and you're right. Both of those, I think, are interrelated. The biggest risk that we have in terms of getting information that's usable certainly from the video element is trying to attain a clean wellbore environment. So the limitations of the system are that we use optics, and we therefore have to have an optically clear environment to get that to work. So just to help illustrate that, I've got a couple of slides that I prepared on this subject to talk you through how we get around that. And it's worth taking a step back and saying that as a service provider, we operate in the high 90s in terms of success rate. So better than 9 times out of 10 when we go to a well site, we help deliver answers that meet the original objective. And that's really a factor of the way that we work, that we don't just turn up and say, right, here's the technology, here's the camera, guys, there's the manual, good luck, tell us how you got on. We actually work as a consultative service. We help look at the well itself, the objectives, the way it's configured, what fluids it may have in there, and we come up with a plan to try and come up with a clean environment that's best suited to get the images that we need at the locations we're interested in. And 2 of the parameters that we look at are, what's in there to begin with, and how could we clean it up if we need to. And the factors that really affect our success are shown on this slide here. That on the left-hand side, we've got some coins here inside a glass of mineral water, and you can see, perfectly the size and even the denomination of those coins. But if you put the same coins into a glass of cola, you can't see anything. And it's not because there's any solids or particulates in the way. It's because there's pigment inside that fluid that absorbs the light and prevents us from transmitting the light from our LEDs and then receiving it back at the camera array. The second factor is about the particulates and clarity of the fluid itself, that we could have a water producer, for example, but if the solids content suspended within it is high enough, then it can cause us problems in acquiring images. And here you can see at varying levels of NTU, the types of images that we can obtain inside the well. And clearly, if we can get down to 20 NTU or better, then we'll have a great chance of acquiring good pictures. So again, knowing this, we'll look at the well, we'll look at the objectives, we'll think about things that we can do that naturally occur in the well. If it's a multi-phase producer, for example, can we shut it in? And if it's a shallow issue, will we get a nice gas cap at the top that will allow us to take the images that we want? Or conversely, if it's deeper down, will we be in a column of water that could potentially be clean enough for us to operate in? And we can float the position of those sections and manipulate them from surface by either pumping water or perhaps bullheading nitrogen, again, to try and get the window in the right area. So as we said, in most cases, and we operate in some wells that are, very, very high rate oil producers with terrible conditions in terms of light quality, and we're able to come up with a plan to overcome that and get the types of images that we're seeing here. And I think just before we check if we've answered that question in full, I also want to stress that the presence of oil is not a problem in these wells. We don't have to clean it up to the extent that there's no longer any oil present. This example is an oil producer, a horizontal well taken from North America. We're conveyed on coiled tubing at the moment, and you can see as we're pushing along the low side, we're sitting in the produced water. But as we go through the natural undulations of the well itself, we go into the oil column, through that, and out into the free gas at the other side. And the way we've prepared our camera lenses with the coatings that we've put on there, we repel the oil very, very quickly. So there shouldn't be any lasting problems with surface conditions, blobs of oil that get stuck on the lens. Any small elements like that, we can simply reciprocate the camera up and down using the wire to clean it up and then move on. So as long as we know the parameters we're working with and we're careful with the way we execute the job, we should be able to get the images that are needed and the measurements from the caliper. And in that case, we've been very successful to date in meeting those objectives. So I just want to check from those that asked the question, does that give you confidence and help address the question that you had?
Yeah, thank you. It was very clear. Thank you.
Okay, thanks very much. All right, well, are there any other questions that have come in, Mike? Anything else we can look at there?
Yeah, there's a couple questions here about the temperature capabilities of both the Optus Infinity and the integrated video caliper. So, so firstly, with the integrated video caliper, it can actually be run continuously at 125 degrees Celsius. So that's 257 degrees Fahrenheit. But it can be pushed up to operate in 150 degrees Celsius for up to 6 hours. So that's 302 degrees Fahrenheit. And for the Optus Infinity, it's continuously able to operate at 125 degrees Celsius. So hopefully that answers your questions there. We've got,
thank you.
Great. We've got one other question here from Emmanuel asking if it's possible to detect leaking connection in the tubing.
Yes, I saw that one come in as well. That's a great question. So what I'd like to do, Emmanuel, if you wanted to have a look at this in more detail, we've got lots of case studies and examples on our website. And I'm just going to click here on the case studies tab. And there's a whole raft of additional ones on our YouTube channel as well, I should say. But if I just come down here, I can actually dissect the case studies by category, and we'll take a little look here at leaks. And specifically to address that question, we've got a clip here that we took a while ago of a connection leak in one of the wells that we operated on. And you can see here the individual gas bubbles coming up through the water that we've got inside the tubing there. We then positioned the side view camera at the connection depth itself. You can see some of the threads that haven't been fully engaged. That's probably intentional. That could be fine. But certainly you can also see the presence of a leak coming through those threads as well. So the sealing elements haven't been affected. They could have been contaminated. But ultimately, yeah, you can see that very clearly that there's a leak here. I should say as well, this is a tiny leak. This is a small number of gas bubbles in a very, very large volume. So other techniques, and including things like acoustic leak detection surveys, which I know very well from a former life, these sorts of things are quite hard to locate. But with combination of those sensors, you can hear it on the acoustic tool, you might be able to detect it on a thermal tool, and you can see it happening with the camera. And all of that you could achieve potentially in real time from a combination service. There were a couple of other leaks examples in there. I think the second one is worth just showing here. This is a much more significant leak that occurred in a horizontal injection well. During a stimulation job, something significant happened downhole. We think there was perhaps a formation movement, and you can see that there's quite a significant leak occurring and some oil flowing on the high side. There's the high side indicator there, top right. This is the top of the well. But as we move down the well, we come to this connection, and this one isn't one that is leaked because it hasn't been made up correctly. This one has started to leak because it's been completely torn apart. So again, significant forces downhole to result in that type of event. Lower down, we also saw some damage to this inflow control device here. That is not meant to look like that, but it's been, again, completely destroyed by the forces downhole. The reason I wanted to bring this one up, and it's particularly useful for those who work in remote operations or even offshore installations. In this example, we trained up the incumbent wireline company to operate our equipment, to link it up together, to do the surface test to make sure it worked, and to help deploy it in the well on their wireline. However, we were controlling the camera in real time from our operations center here in Aberdeen, streaming the images to ourselves and to the customer so they could see what was happening. And that's a fantastic way of achieving an efficient operation with minimum POB, minimum fuss and mobilization, especially when we have travel restrictions as we do at the moment. But also it's a great way in having that real-time decision making, that not only are we seeing what's going on, but the well operator themselves can see it. We're speaking to them over the internet exactly as we are today, and we're taking decisions on the fly. So another great example there. Okay, well, I'll just park that there to say, again, there's a whole range of other case studies there. There's a few other questions I think that are coming through. We've got some questions about the size of the tool. I think the best thing there is we can follow up with data sheets for all of these items and typical tool string assemblies. But the tools themselves, the cameras, are typically 43 millimeters or 1 inch and 11/16. So depending on what else we're combining them with, they're very, very slim, very lightweight, and very easy to ship around. Mike, any other questions there?
Yeah, we've got one here asking, what is the highest deviation that you've ever deployed the camera at?
Well, that's a good one. I'd have to check, but I remember seeing a number of clips with video tractors, video whilst tractoring, even some coil work where we've been going significantly uphill. So we've pretty much done it all. And with the flexibility we have on conveyance, it could be gravity deployed. We do a lot of pump down work in the US, of course, for the plug and perf frac market. But again, with that ability to physically see what's going on in real time whilst tractoring, this has been a terrifically successful service in and around the North Sea, Gulf of Mexico, places where there are deep, long horizontal wells.
Yeah, I've missed one question here from Oscar Cortez. He's asking, based on your experience, does the tool perform better when conveyed on coil or with E-line tractor in case of extended reach wells?
Oh, that's a great question. I'm not sure that I'm probably the best person to answer that. And I suspect it really depends on the application. But again, we've run on all different modes of conveyance depending what's available at the well site. Some of our most advanced studies that we do, not necessarily for corrosion, actually for evaluating perforations, we do on very, very simple generic coil tubing. And those are long reach horizontal wells, as we said, multi-stage plug and perf hydraulic fracture wells, and the results are excellent. On the other hand, we do a relatively significant amount of work in, let's say, places like Sakhalin, for example, where they have extremely long lateral sections. And we work there on wireline tractors, seeing the video in real time, and then also recording surveys as we pull out of hole. So I don't think we're particularly limited there. I wouldn't say there's a better way of conveying one over the other. It's really about what you have at the well site and potentially what else is happening in your operation. Do you have any pumping operations or production solutions you're trying to achieve? In which case, we'll piggyback on the coiled tubing that you've got. So yeah, I think total flexibility, but I wouldn't say we're leaning one way or the other.
Okay, and we've got one here from Didier, just asking if we have any capacity limitations on the memory of our Optus Infinity camera.
Yes, another good question. We have a time limit for the memory storage. That's true, and that gives us, I think, 10 hours as it stands today with the compression that we're using into the memory controller. We improve that all the time as we update the software to go with the tool, but 10 hours for most surveys has been more than enough. In some extreme examples, and really long wells we've been in, we've actually stacked 2 cameras into the assembly and had them on a timer with a delay, so that one camera can record for the first interval, then the second camera will slightly overlap and record for an extended interval. So in that sense, we've been able to double our capacity in the same run. I think, though, the most interesting development that we're working on, which we're about to field trial, and we have tools on the way to Canada at the moment for some early work on this, is what we call our hybrid memory system, where we're able to see one of the cameras, whether it's the downward viewing camera or one of the 4 array cameras, in real time. And that allows us to do very instant spot checks of what's going on and take a view of the well around us. But then on command, we can tell it to record all 4 cameras into the memory system over whatever interval we like. So that way we can be very selective over the areas that we capture the detailed images over, and we can skip past let's say the less interesting or the more benign areas and focus on the particular problems so that we can get the best possible data quality there.
Okay, and we got one question here from Frederick Reisler, asking for a rough estimation of the cost of a well intervention. I would say it's proven to be cost effective, but I think that the best thing would be to for us to reach out to you to discuss your specific requirements and any challenges you might have. So that's what we'll do there. And we've got one final question, which I think you answered there, Tobben, about our real-time cameras. Yes, we do have cameras that are deployed on electric line there. So that's it for the questions in the chat window.
Hey, Mike, there is a question that just popped in there.
Oh yeah, another one from Frederick. Colored picture in the future? Yes, we already have full color cameras. Like I say, it's full color. It can be on E-line. So yeah, we'll reach out to you, Frederick.
Yes, apologies. I could have made that clearer in the presentation. The cameras that we have, as Mike says, are full color. The challenge is a lot of the wells are completed with some very grey looking steel, so it doesn't necessarily come through on the images we've shown. but here on these test cards that we use in the workshop and at the well site just to check functionality, you can see that we're actually recording full color all the time in there. Yeah.